think it's probably really valuable at this point to summarize everything that we've proved and discovered. The first thing we proved and discovered is that if you have some kind of integral, which is a function of a set of variables and a set of their derivatives, then to maximize or minimize this integral, these functions must obey, and these are called the Euler-Lagrange equations. That's a set of equations, a set of n equations. Now what's hard about doing these kinds of problems is first of all setting up the thing you want in terms of that integral. So you had a couple of goes at setting that up, and we should have a couple more to practice that, and there's one in your assignment. Actually, computing this is of course straightforward. A computer can do it, but then you end up with a second order differential equation which can sometimes be quite difficult to solve, and again in extremis we resort to computers or even numerical solutions. There is one simplification you can make in the situation where the function f doesn't depend explicitly on x. In other words, partial df dx is 0. That's called the function is autonomous. And in that case, we have the Beltrami identity, which is that this function here is a constant. So that's the mathematics that we've learned. We've also learned some physics. So we learned that the Lagrangian, which we defined as the kinetic energy minus the potential energy, we discovered that if we wrote the Lagrangian in any set of coordinates that we liked, those coordinates always followed the following equation of motion. And that equation of motion was extremely suggestive. That equation of motion told us that what's really going on is that there's probably some key physical quantity, which is the integral of this Lagrangian, that is being a maximum or a minimum. And in fact, this is called the principle of least action. The action is defined as the integral over time of the Lagrangian. And the Lagrangian can be a function of all the sets of generalized coordinates. Remember, the original coordinates could be used as generalized coordinates if they're not constrained. All their derivatives, and possibly time explicitly. This is the action, this integral of the Lagrangian, that is minimized, and this is called the principle of least action. It's also known as Hamilton's principle. And an important thing to add is that if we were to start here, if we'd have started with the principle of least action, then we would have found this entire business of going through constrained systems that was quite onerous when coming from Newton's laws. We would have found it completely trivial. And the reason for that is, if the action is minimized in some space, then if I restrict how I can move through that space, I don't really change the principle. I still have whichever of paths I have allowed left, I still have to choose the one that gives me the least action. And so I can write down my principle of least action in exactly this form immediately, straight from the larger one. And the principle of least action is important through field theory, it's important through classical mechanics, it turns out to be an emergent property of quantum mechanics, which we'll see, and therefore the action is also a vital quantity in quantum mechanics, and indeed when we start marrying relativistic mechanics and quantum mechanics together, it's one of the absolute bedrock principles in all of physics.